Most people are somewhat aware of what an atom is and accept that they make up the things around us. But for a long time, atomic theory was controversial. And to understand chemistry is to understand the process by which these particles and their components came to be accepted knowledge.
Democritus was an ancient Greek pre-Socratic philosopher from Aldera, which was known for his formulation of atomic theory. Democritus argued that matter was subdivided into invisible and immutable particles that changes its appearance and separated from other particles. So therefore, he concluded that an atom are tiny and cuttable and a solid particles which are moving at random. So there are four principles or claims that compose Democritus' atomic theory. First is all things are composed of the atomos or the fundamental particles atoms. Second, atoms cannot be destroyed. Third, atoms are separated by the void or empty space. Last one is atoms are in constant motion and undergo constant charge through the void. Democritus made several key contributions to atomic theory. First, concept of atoms. He introduced the idea that everything is composed of small, indivisible particles called atoms which are eternal and unchangeable. Second, variety of atoms. Democritus proposed that atoms differ in size, shape, and mass, explaining the diverse properties of matter. Third, the void. He suggested the existence of a void, or empty space, through which atoms move allowing for the formation of matter. Fourth, indivisibility. Democritus argued that atoms cannot be divided further, a concept that underpins the modern understanding of atomic structure. And the last one, philosophical implications. His ideas encourage a shift from mystical explanation of matter to a more rational, scientific approach, influencing later philosophers and scientists. These contributions laid the groundwork for future developments in atomic theory and the field of chemistry.
John Dalton, a British school teacher, published his theory about atoms in 1803. His findings were based on experiments and the laws of chemical combinations. It involves the following postulates. Number one, all matter is made of atoms. Atoms are invisible and indestructible. Number two, atoms of a given elements are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. Number three, compounds are formed by a combination of two or more different kinds of atoms. Number four, the atom is the smallest unit of matter that can take part in a chemical reaction. Number five, in chemical reaction, atoms are combined, separated, or rearranged.
J.J. Thomson is known as the father of the electron. In the late 19th century, a groundbreaking physicist named J.J. Thomson revolutionized our understanding of the atom. Born in Manchester, England in 1856, Thomson dedicated his life to exploring the mysteries of electricity and matter. One of Thomson's most significant experiments involved cathode rays. These are streams of charged particles emitted from a negative electrode in a vacuum tube, passing these rays through electric and magnetic fields. Thomson was able to study their properties. In 1897, Thomson made a groundbreaking discovery. He found that cathode rays were composed of tiny negatively charged particles. He named these particles electrons. This was the first time that a subatomic particle had been identified. Thomson proposed a model of the atom known as the plum pudding model. In this model, the atom was envisioned as a positively charged sphere with negatively charged electrons embedded within it, much like raisins in a plum pudding. While this model was later superseded by the nuclear model, it was a significant step forward in our understanding of atomic structure. J.J. Thomson's discovery of the electron had a profound impact on the field of physics. It paved the way for further research into atomic structure and led to the development of modern atomic theory. Thomson's work also had significant implications of the fields such as chemistry, electronics, and nuclear physics. In recognition of his groundbreaking contribution, J.J. Thomson was awarded the Nobel Prize in Physics in 1906. His legacy continues to inspire scientists today. Thomson's discovery of the electron marked a turning point in our understanding of the universe and laid the foundation for many of the technological advancements we enjoy today.
Rutherford is known as the father of nuclear physics. His most notable contribution to atomic theory came from his gold foil experiment in 1909. In this experiment, Rutherford bombarded a thin sheet of gold foil with alpha particles and observed how they were scattered. So based on this experiment, he also made several conclusions that is very important in today's times. During his discovery of the nucleus, he proposed that atoms consist mostly of empty spaces with a small, dense, positively charged core at the center. This disproves the previous plum pudding model by J.J. Thomson, which suggests that electrons were evenly distributed throughout a positively charged sphere. Next, we have the nuclear model of that. Rutherford's model suggested that electrons orbit the central nucleus much like planets around the suns. While his model didn't explain the specific behaviors of electrons, it laid the foundation for future research.
Niels Bohr. Niels Bohr is a Danish physicist. He revolutionized our understanding of the atom and laid the foundation for modern chemistry. In 1913, he introduced the Bohr model, which described the atom as a small, positively charged nucleus surrounded by electrons that orbit in distinct energy levels. This model was groundbreaking because it explained how atoms emit and absorb light, a key aspect of chemical behavior. Bohr's theory built upon quantum mechanics, proposing that electrons could only occupy specific orbits or energy level, and when they moved between this orbit, they emitted or absorbed energy in discrete amount, known as quanta. This helped explain why elements emit light at specific wavelengths, lead to the development of spectroscopy. His model clarified the structure of the periodic table and why elements in the same group behave similarly in chemical reaction, as their outer electron configuration determined their chemical properties. James Chadwick. In 1932, British physicist named James Chadwick made a groundbreaking discovery that changed the world of physics and chemistry forever. He discovered the neutron, a subatomic particle with no electric charge residing in the nucleus of an atom alongside proton. Before Chadwick's discovery, scientists believed the atom's nucleus contained only positive charged proton, but the neutron explained why atomic mass didn't align with the number of protons alone. This finding revolutionized our understanding of atomic structure, leading to major advantages in nuclear chemistry. Chadwick's discovery of the neutron also paved the way for the development of nuclear energy and atom bomb, as neutrons play a key role in nuclear reaction and fission processes.
Erwin Schrödinger's main contribution came in the 1920s with his wave mechanics and the Schrödinger equation, which are key elements of quantum mechanics. He extended the atomic model by addressing the behavior of electrons in more detail. First, we have the wave-particle duality of electrons. Schrödinger proposed that electrons do not move in fixed orbit, such as what Rutherford's model suggested, but instead, it exists in a cloud-like regions or probability where their exact position cannot be determined. This introduced the idea of the electron having as a both particle and a wave. Second, we have the Schrödinger's equation. He developed this mathematical equation to describe how the quantum state of a physical system changes over time. This equation provides a way to predict where an electron is likely to be found around the nucleus in terms of probability distributions, called the orbitals.